Welcome back. For our third and final portion, part 3 of session 20 on absolute maximum shear stress, we're going to discuss some examples that involve some of the structures we've discussed previously in the class. We're going to discuss what we've discussed, yes. So up to this point, we've talked about how you would find the condition of triaxial stress, those principal stresses associated with triaxial stress, the absolute maximum shear stress with Moore's circle, and now we're going to talk about using Moore's circle to calculate absolute maximum shear stress with structural examples. In this example, we have a spherical pressure vessel, and if we say that it has radius r with a wall thickness t and internal pressure p, we can write out this equation for the symmetric stress, right? This is like sometimes what Hibbeler calls it sigma 2, because it's not sigma 1 associated with the hoop stress in a cylindrical vessel, but it's the stress that is associated with a spherical pressure vessel. Now, if we plot Moore's circle, what does this look like? And this was kind of on the last homework. For just looking at the in-plane, right, representation, Moore's circle becomes a dot at PR over 2T, right, for in-plane, because we're saying there's no shear stress, and we're saying that we have a situation where, like if you have a sigma x and a sigma y, any of them, these are always going to be the same. If I rotate the element, okay, about it's a normal coming out of the sphere. So that's Moore's circle, all right? If we just look at the in-plane representation. But remember what we said for these thin-walled pressure vessels: sigma 3 is equal to 0. So we can write that out. We can say, all right, sigma 3, you're equal to 0, and then we put that dot at the origin. What does that mean? That means that now we have a representation where we can draw a Moore's circle. Okay, before where it was just a dot, and it turns out, well, Moore's circle tells us that there is a shear stress, okay, that's related to the, if this were x and y, it's related to the xz or the yz planes, right? When I say x and y, if I were to say like this sigma and this sigma are in the xy plane. So with that information, we can figure out, oops, I went a little fast. We can figure out what the maximum shear stress is, and it's going to be it's going to be the radius, and the radius is half the diameter, which we can tell to be PR over 2T here. Okay, so the maximum shear stress that this spherical pressure vessel the absolute maximum shear stress it would experience is PR over 4T. Here is a question for the homework, okay? It's looking at the cylindrical pressure vessel, and we're asking what is the absolute maximum shear stress. And the final question for this session is a return of a problem from session 16. And here we're saying that A is on this portion of this loaded shaft or beam with a bend, okay? And that is on the outer surface. Okay? So if you go back, this is now a repeat. If you go back to session 16, what you can look at are the contributions of these different forces, Px, Py, Pz, onto these kind of different representations or these different plates that are at A, where A is on the side. And if we look at the contributions from Px, Py, Pz, and I invite you to go back to session 16 if you want, you can see that sigma x is equal to px over A minus pxb times quantity C over I. So we're getting some axial loading and we're getting some bending stress potentially. We have our contributions from Py in terms of a torque, okay, and we have contributions from Pz also going to be in terms of a torque. Okay, should have mentioned that since A is on the effective neutral axis, it also contributes shear force. And there is no bending stress because A is on the neutral axis. Okay, so here we have contributions from Pz. Okay, and this, like I said, is going to be contributing a torque to the system, and we can give it as such. But there's no transverse shear because A is kind of on the outside. All right, so if it's on the outside, that means you have maximum bending stress. But if it's on the outside, you have essentially no transverse shear stress. And this is also directly from the previous assignment, and counting up the contributions from Px, contributions from Py, and contributions from Pz. These calculations, and then being able to put the normal stresses together and the shear stresses together, and that's what you see here. So if we were to plug in numbers for this expression, we should be able to figure out sigma x and tau xy, and then be able to look at calculating out a state of or a condition of principal stresses where we have one of the principal stresses being the largest possible. This session was probably on the shorter side, and I'm glad that you were able to get to this point and stick with it. We have covered a technique or two for finding the condition of triaxial stress. We've looked at calculating absolute maximum shear stress with Mohr circle, and we've also looked at calculating absolute maximum shear stress with structural examples. Thank you for participating, and if you have questions, just let me know.